I'm rather surprised that it happened in my lifetime. I certainly had no idea that it would happen in my lifetime at the beginning, more than 40 years ago, because at the beginning people had no idea about where to look for it. So it's really amazing for me to find out that it's really enough, shall we say, enough for a discovery claim. I think it shows amazing dedication by the young people involved with these colossal collaborations to persist in this way on what is really a very difficult task. I congratulate them. The story begins with the work of Nambu and Goldstone in 1960. I asked myself, well, what would happen if we combined the Maxwell type of field theory with some of these models which involved spontaneous symmetry breaking? So I simply put together a model theory, a very simple one proposed by Goldstone in 1960, and I married it to Maxwell electrodynamics. And at that point, I saw in the equations of the theory that what happened was that what would otherwise have been the photon became a particle of spin 1 with mass. And the way it happened was that a photon has essentially two spin states, two polarization states, but a massive spin 1 particle needs three. The missing state is acquired from what were previously Goldstone bosons, so it all becomes an acceptable kind of physical description. So then I wrote a short paper about that, and I sent it off to Physics Letters, whose editor was at CERN, and they rejected it. And at that point, I thought maybe the paper was too short, and I hadn't said enough. The paper was about one side of A4, so I thought I'd better look at what were more physical consequences of this kind of theory. And I pointed out in a revised version that there would always, in this kind of theory, be some leftover spin 0 particles which did have mass, and these are what became known as Higgs bosons. But there was nothing particularly new about that. It was just that I drew attention to them. But the same sort of excitations occur also in superconductors and were actually observed experimentally as long ago as 1980.
Of course, I'm very happy of that. The result now is really extremely impressive, and I am full of admiration of what CERN has realized. It certainly is important because it confirms essentially most of what has been done in physics, at least the physics which is not speculative and trying to understand things which for the moment we cannot verify, but for most of the physics which is has been verified, this is extremely important because it really is the stone that shows that everything is in place.
Well, this is a culmination of a search which has been going on for some time now. It is going to be an achievement, I trust, which results in the verification to a very high degree of accuracy, what we call the standard model. This missing scalar boson has been perplexing us for some time, and the fact that the data now seem to say that we're on the threshold of a major discovery is incredibly gratifying and exciting to be here, and gratifying because I've had the privilege of being associated with this. It is very exciting and very commendable. It shows that the people who put this machine together did an excellent job. And some of my colleagues have remarked about how amazingly trouble-free this machine has been.
Well, it's really marvelous. It's very gratifying to realize that an idea and a theory that we worked on nearly 50 years ago has such huge relevance to actual physics. When we started working on this model, in fact, much of the original work comes from my PhD thesis at Harvard, and in fact that's when I started talking to Professor Hagen. But when we started working on it, we had no idea that it would be more than an interesting model. But when we finally solved it, working with Professor Kibble, we knew that we had indeed done something that was very different and was very exciting, but we still didn't expect it to have anything to do with physical reality. It's very gratifying to know that model really was right, and it shows, certainly to us, the value of just imagining and just trying to follow the leads that you get from simple ideas, that it's worthwhile doing this and seeing where you come out. It was really fun for us, and now we see that something really important has happened from those ideas. We developed that entire theory. We were amazed at the results. We were told that we were wrong. I was even told, I don't think Professor Hagen actually heard the conversation, but I was told by Heisenberg that I was wrong, which was pretty scary for a young man who wanted to get a job. But we very carefully studied the theory. We were convinced when we published it that we'd covered all possibilities that we understood of the theory being wrong. We had done many consistency checks, and we were sure it was right.